The purpose of this video is going to be to continue building our island biogeography spreadsheet, and we're going to do two things. First, we're going to explore this concept of turnover rate and look at how changes in these maximum immigration rates and maximum extinction rates affect our equilibrium number of species. Jed alluded to that in his lecture. And then the second goal of this spreadsheet exercise is to add in the effects of area and distance into our island biogeography equations. So let's start off with the first part, which is just simply calculating the turnover rate. So to recap where we've been, we have a mainland of 30 species, we have the maximum immigration rate of 6 and the maximum extinction rate of 4. And we've calculated the slopes for these lines as a result of those three inputs. And from those, we're able to calculate what is the slope, what is the immigration rate for an island that has a particular number of species. And we've been using the number 6. So at 6 species on the island, then our immigration rate should be 4.6. and our extinction rate should be 0.8, and that results in higher immigration rates than extinction rates, so we're going to be adding 4 species in the next time step. The equilibrium number was computed through the equation that Jed shared with you. And if this is the equilibrium number at 18, the turnover rate is just the y-intercept. So the x-intercept, where these two lines cross, provides you with the equilibrium number of species, but the y-intercept at that point provides the turnover rate. So that rate is how many species do we expect to change in terms of our island ecosystem. So we know there are 18 species present, but at each time step there may be a different assemblage of species, and that turnover rate is helping us to understand how many new species are there with each different time step once we are at equilibrium. And Jed talked about how to calculate that turnover rate, and it is just the maximum immigration rate times the maximum extinction rate, so that's in the numerator, and I'll put those in brackets, the maximum immigration rate times the maximum extinction rate, and then that whole thing is divided by those two portions added together, so the immigration rate plus the extinction rate, and that gives us our turnover rate, which is 2.4. To answer the question about how do changes in this rate, the maximum immigration and maximum extinction rate, affect our overall equilibrium number of species, we've set up a data table. And remember, the data table has a particular structure. We're going to feed in these values for the maximum immigration rate, and we're going to feed in these values into the maximum extinction rate. And for each of those combinations, we're going to compute the equilibrium number of species. And that main output needs to be stored in the upper left or the upper left corner of the data table itself. So here we're going to simply reference our equilibrium equation. Let's take a look now. We can grab all of the cells in the data table and then head up to the Data tab and then go to What If Analysis, Data Table. Our inputs along the row will feed into the maximum immigration rate stored in cell C4, and the data values down the column will be fed into the cell stored in cell C7. And if we press OK, the data table will be filled in, And we'll be able to look at the equilibrium number of species under these different conditions. So this data table is a wonderful tool for helping you to see how different combinations of these inputs would affect the equilibrium rate in one nice image. I've added some color coding here with the conditional formatting tab so that the larger numbers are formatted in green and the lower numbers are in red and orange. So you can see and verify some of the things that Jed mentioned in lecture. If we have the maximum immigration rate go up, then our island equilibrium number is going to be higher because these individuals from the species pool are really vagile. They're able to really populate and colonize that island. However, it's tempered a bit when the extinction rate on our island is also high. So the higher the extinction rate becomes, the lower it's going to drop that equilibrium number of species. So the best case scenario, our island will be absolutely full of species when its own extinction rate is 0, and when the pool of dispersers is very vagile and is able to colonize our island. On the other end, for example, if our extinction rates are pretty high and our immigration rates are pretty low, then we are expecting our island to have very few species, really low number of species, because it rapidly loses species due to extinction and because the pool is not able to colonize and provide new immigrant species to our island. Now let's change gears. One of the big adjustments that we make to this model is the incorporation of information about the area of the island and how far that island is from the main species pool. And we can enter some numbers in here. So it's 200 units of area, and I'll let that stay dimensionless, and 300 units of distance from the mainland. And the big idea here, and this is part of the MacArthur and Wilson model, is that these rates really are tempered depending on how close you are to the mainland and how big you are as well. And so, as Jed pointed out, as the area of the island increases, it's going to dampen this extinction rate, under the assumption that large islands have larger population sizes and it's harder for those populations to go extinct, and therefore it's harder for the species to go extinct on that island. Distance is another factor, and the distance might be affecting the colonization rate. And the idea there is that if you are very close to the mainland, your colonization rate may go up. And as you are very far from the island, your colonization rates might go down. So those two things are tempering these immigration rates and these extinction rates. Here is the area, and we need to add in an effect of area, and we're going to store that effect in cell C9. And I'm going to enter 0.25 for that value. Here is the distance our island is from the mainland, and in order to adjust our colonization rate, we're going to need to enter an effect. What effect does this distance have? And we'll enter the value 0.01 in cell C6. Now, the adjustments we'll make to these rates are actually pretty simplistic. So we're going to write the word adjusted here, and we're going to be calculating some new outputs. So let me get those set up for us. And we'll be calculating our adjusted immigration rate and our adjusted extinction rate, and they're simply just going to be adjusted by the area effect and by the distance effect. And these adjustments are pretty simple. for the immigration rate, we're going to let that be a function of how far the island is from the mainland source. So we're going to take our actual rate and then we're going to adjust it, divide it by the actual distance that cell is, or that island is, from the mainland, and I've named that cell distance, and we're going to multiply it by the distance effect, and I've named that cell d scale. So it's just a scaling effect on distance, so it's just a constant, and so now we can see that for this entry and given our distance, now our adjusted lambda for immigration is now down to 1.6 species per time step. Make sense? Now how about the extinction rate? Well, similarly, we're going to make an adjustment to our original extinction rate. So it's going to be cell F7 adjusted by, divided by, and here we're going to take the area, which I've named area, that cell is named area, and we're going to raise it to cell C9, and I've named cell C9 A scale, which is just the scaling effect on area. So we actually don't know what these are, and we can do studies to try to calibrate what these values actually should be. But for this particular system, I am now adjusting my immigration rate, which originally was 4.8, and with the adjustments which is due to how far that island is from the mainland, we end up with a rate of 1.6. And similarly, we start off with our original extinction rate, and after we adjust it for the area of that island, now it is going down to 0.21. So that is the notion of adjusting by area and distance, and those are two key parts of the theory of island biogeography. We can compute delta S, our change in the number of species per unit time, the same way we did before, by just subtracting those two rates. And so you can see that that's quite a difference. Now, how do we calculate this new equilibrium number of species with these adjusted parameters? Well, let's take a look at how we computed equilibrium before. This was derived in lecture, and so we haven't described it, but basically we took the maximum immigration rate and multiplied it by the species pool, and then we divided it by the maximum immigration rate plus the maximum extinction rate. Now, we can use that formula, but the problem here is that since we've adjusted these rates, these maximum values no longer can be used. So we need to do a little bit of manipulation here to recompute what our maximum values are going to be. And I'm just going to label those max. So we're looking for the maximum immigration rate, and that will be computed in cell H6. And then we're looking for the maximum extinction rate, and that will be computed in cell H7. Once we have these two rates, we'll be able to simply use the exact same equation we used here, but now compute our equilibrium species with these distance and area adjustments. Now this is going to take a little bit of thought here, and let me use some space over here to help us walk through our problem here. So here we were computing our immigration rate, and let's just click on that, as the intercept plus the slope times the number of species. So let me write that out just like so. So lambda, our number of species at a particular time step, is equal to the maximum immigration rate, that's our intercept, plus the slope times the number of species. Now we can't use this slope, so we're going to end up replacing slope with what we originally calculated it with, and that is going to be negative max I divided by the pool. So let me write that and replace this slope with its original equation. So here we go. I've just replaced the slope again with the maximum I divided by P. And then the next step then is to solve for what I max would be. And there are a few steps involved here. I'm just going to cut right to the chase and give you that result. And we'll play around with this derivation in the sandbox. And here it is. The maximum I is equal to the lambda value times P, the species pool, divided by the difference between the species pool and our current number of species. And we want to set this up here because we want to use our new lambda value, which we just computed. So let's enter this equation here. So max I is equal to lambda times P, the species pool, divided by the sum, or the difference between the pool and the number of species present. And let's go ahead and just add in some parentheses to make sure our order of operations is correct. And we end up with a maximum rate, a maximum immigration rate of 2 species per time step. Now we need to do a similar exercise for extinction, and let's work through those equations here. We know that the extinction rate originally was computed as the slope times the species present. So let's start by writing that simple equation. Here it is. The extinction rate is a function of the slope times the species present. Now the slope, we don't want to use this slope. Instead we want to replace the slope with its original calculation, which is equal to the maximum E divided by the species pool. So let's add that in. We've replaced slope now with this original term, E max divided by P. And now we just need to reorganize this and solve for E max. Let's do that. And we end up with E max is equal to P, the species pool, times mu divided by S. And let me make all of these a little bit darker so you can see these equations, and I'll blow those up a little tiny bit. So here now we have a formula for calculating I max, which we've done here, and E max when we use these adjusted rates. So let's enter in cell H7 the E max under these adjustments. So that's going to be the species pool times the extinction rate mu divided by the species present, and we end up with 1.06. So that gives us our correctly adjusted maximum rates for the island biogeography model, where we consider area and distance into our equations. At this point, we can use the formula that we used here to calculate the equilibrium number. The equilibrium number is equal to the max I times the pool, that's in the numerator, divided by max I plus the max E in the denominator. So let's write that with our new values. So the numerator is the maximum immigration rate times the species pool, divided by the maximum immigration rate plus the maximum extinction rate in the denominator, and we end up with 19.6 species. So you can see here the idea is that under the equilibrium model, we end up with an equilibrium number of species. But with these adjustments, and the adjustments consider the area of the island and the distance from the island, we can see that that adjustment will change the equilibrium number of species. And we set up another data table to explore this concept. So the first data table did not include area or distance effects. Here we're going to let the distance to the mainland and the distance to the area of the island change, and we're going to explore how those changes will affect our equilibrium number of species. So let's use our data table to do this. I'll try to shrink my sheet back up a little bit. Our reference here in our left corner of our data table must refer to a value, and we're going to tag that to the equilibrium number of species with the adjusted model. So once again, we're going to select our entire data table. We're going to go to the Data tab, choose What If Analysis Data Table. Our row inputs are going to feed into distance. So they're going to feed into cell F5. And our column inputs are going to feed into area in cell F4. And the table then should be populated. And we've again color-coded these, actually with the reverse color scheme. I'll change that. And the green represents the higher equilibrium number, and the red represents lower values. And this is a nice way to compare both of these scenarios. So the top set are the rates that we would expect without the distance and area effects, and the bottom graphic shows the rates that or the equilibrium species numbers that we would expect with these area and distance adjustments. And we're going to have plenty of time to explore these concepts in the sandbox, because this is really one of the most popular and important theories with respect to the number of species and what factors might control the number of species that we observe in different islands. And as Jed mentioned, these islands can be actual islands in an ocean, but we also have used this theory to think about islands like islands of patches in a sea of inhospitable habitat. And so it's become a popular framework for investigating habitat fragmentation issues. And that certainly is one of the topics of conservation biology that we need to be aware of. So I'll pass you back over to Jed for some closing thoughts, and we'll be able to really play with this model a lot more in detail in our homework section. See you later.